Hello and welcome to my video. So my name is Christy Hazel and I'm a postdoc in the algebraic topology group at UCLA. So in this video, I'm going to tell you about equivariant fundamental classes in ROC2 graded cohomology, which is some work from my thesis project. So just to start, let me give you a very quick introduction to ROG graded cohomology. So here G is a finite group. And we're going to be working in the world of GTOP, so topological spaces, together with an action, a continuous action of the group G. In this world of GTOP, we have these nice spaces called representation spheres that are going to play the role of our Sn. So given a finite dimensional real orthogonal G representation, we can form the one-point compactification, so add a fixed point at infinity. And this gives us a sphere whose dimension is the same as the dimension of our representation, and our sphere also inherits a nice action of G. I'm going to use this notation S to the V to denote the one-point compactification of V. Okay, and using these equivariant representation spheres, we have equivariant suspensions. So if X is some base G space, I can form the V suspension of X by smashing with SV. Okay, today we're going to be talking about Bredon cohomology. This is our analog to singular cohomology in the world of GTOP. So this is written very similarly. I have some sequence of functors, H alpha, with coefficients in M. Here, alpha, though, is an element of ROG, so the Grothendieck group of finite dimensional real orthogonal G representations. To maybe just provide a little bit of motivation why we might grade on this. This is a cohomology theory, so we should have suspension isomorphisms. But really, we want these suspension isomorphisms to be with respect to this equivariant suspension. So I would want H alpha of X to be isomorphic to H alpha plus V of the V suspension of X. Okay, if I'm grading on ROG, this alpha plus V can really be made sense of in that group. Okay, and then this M here is what's called a Mackey functor. If you don't know what a Mackey functor is, it's our analog to an abelian group in this equivariant world. And very roughly, it's a choice of an abelian group for each orbit, so for each G mod H, together with the data of maps between these abelian groups. Okay, so now I want to specialize to the case when G is the cyclic group of order 2. So then any such representation V splits as a direct sum of some number of sign representations and some number of trivial representations. I'm going to use this motivic notation RPQ, where RPQ is the representation with Q sign reps and whose overall dimension is P. So if I'm P dimensional and have Q sign reps, that means I have P minus Q trivial. Okay, what we're really seeing is our ROC2 graded cohomology can be regarded as a bi-graded theory. When I talk about these two gradings, I'll refer to this first one, so our P, as the topological dimension, and then this Q, the second grading, as the weight. Okay, and I'll also use this bi-graded notation for our cohomology groups, our Bredon cohomology, and for our representation spheres. So here are some concrete examples of representation spheres for the cyclic group of order 2. So maybe just to go through the first two, S1, 0. This means I take a one-dimensional rep with 0 sign reps. So that's the trivial representation, so R1. I add a fixed point at infinity, and I just get a circle where all of the points are fixed. Here I'm drawing the fixed set in blue. If I look at S11, I'm supposed to take a one-dimensional representation that has one sign rep. So that's just the sign rep. So we have a real line with a reflection action. We add a fixed point at infinity. This gives me an S1 with a reflection action. So I have two fixed points coming from the origin and from infinity. Okay, and then S21, I can leave for you to think. Okay, and for the rest of this talk, we're just gonna think about one Mackey functor, which is the constant C mod 2 Mackey. Okay, so if you're not super comfortable with Bredon cohomology, you can think that we have some analog of singular cohomology for C2 spaces. This analog is now bi-graded. The first grading is kind of like the grading we're used to from singular cohomology, and this second grading is here to kind of record something about the action. And then we're going to be working with the analog of Z2. Okay, the one last piece of background I need to give you is the cohomology of the two orbits. So let me start with the cohomology of a point, which is our fixed orbit, our C2 mod C2. So this is a bi-graded ring, so I can record information about it on a grid. So here P is my topological dimension, Q is my weight. And here every dot indicates a Z mod 2. So for example, H00, in this box up and to the right, I see a dot. So H00 of a point is Z mod 2. H01 is Z mod 2. The H10 is 0. So there's nothing there. Okay, now we'll go through the full details, but roughly we have these elements, tau and rho, and this top portion is polynomial in those elements. So vertical lines are multiplication by tau, diagonal lines are multiplication by rho. Okay, and I also have this element theta down here in bi degree 0, -2, and theta is infinitely divisible by rho and tau. So I also have this whole bottom cone with all these rho multiplications and all these tau multiplications. Okay, I'm not going to tell you how you get this computation. We're just going to take this as a black box for this talk. But here it is. So this is some non-Noetherian ring. I'm going to remember if X is any C2 space, then I always have a map from X to a point where I just crush everything to a point. That's equivariant. And so the cohomology of any space X is a module over this M2. So I get a map the other way in cohomology as usual. So we'll be talking about the M2 module structure, the cohomology of various spaces, and the M2 algebra structure. Okay, so the last thing I have on this slide is the cohomology of the other orbit, so our two swapping points. This cohomology is drawn here. I have this tower of Z mod 2s and weight 0, and this is depicting the M2 module structure. So I have all these tau connections, so all these Z2s are connected by an action of tau. Okay, in practice, it's kind of annoying to draw those big bulky pictures, so we'll be drawing these abbreviated pictures, so just the outline for M2, and then just a straight line for A0. And we'll be seeing these modules throughout the talk. Okay, so I want to give you some prologue to this equivariant fundamental classes story. So overall, our idea here is, given a C2 manifold, our goal is to understand Bredon cohomology classes using equivariant submanifolds. So to make this connection between geometry and algebra. In order to do that, we should have some examples of C2 manifolds and some computations so we can kind of get an idea for how we might expect these classes to work. So giving some background, in 2016, Dan Duggar classified all C2 surfaces up to equivariant isomorphism using equivariant surgery. Using his classification, I was able to compute the cohomology of all C2 surfaces in both constant Z2 and constant Z coefficients. And these computations are as modules over the cohomology of a point. And these examples in constant Z2 coefficients are really what kind of motivated this work. So all of our examples here will be C2 surfaces, even though these fundamental classes really work for C2 manifolds of any dimension. Okay, so let's see a couple examples for what we might expect. So here's a torus with a reflection action. So I'm reflecting the two halves of my donut. Here I've drawn the fixed set in blue again. So the fixed set is two disjoint copies of S1. Over here on the right, I've drawn the cohomology as a module, an M2 module. This is a free M2 module, and there's 4 generators. Maybe I'll just quickly say the topological dimension of these generators should not be surprising. So I have something in 0, 2 generators in topological dimension 1, and 1 generator in topological dimension 2. Okay, and this exactly matches singular. What's more mysterious is what these weights are and how we could have guessed those by looking at this picture. So the answer the question we want to answer is how do we connect this algebraic data to this geometric data over here? I'm going to be able to point at submanifolds or other geometric properties here in order to predict certain algebraic structures over here. Okay, let me remind you how we do this in the non-equivariant setting. So here is just a torus, no action, just a non-equivariant torus. Its singular cohomology is Z2 in degree 0, Z2 squared in degree 1, and then Z2 in degree 2. Okay, and then we have these two interesting codimension 1 submanifolds. So I have this circle that goes around the handle, and then this circle that goes around the donut hole, or the hole of the torus. These two interesting codimension 1 submanifolds are supposed to correspond to this two-dimensional vector space in H1. So we get these two classes in the cohomology of the torus that correspond to these submanifolds. Even better, these classes help us understand the multiplication. So if I want to take these two classes and multiply them together, then these fundamental classes have a very nice intersection product. So this cut product is just given by the transverse intersection, which exactly is this point X, which generates this Z2 here. So what we're seeing is these two generators in H1 multiply to give the generator here. I can also use this intersection product to figure out what C prime squared is. Well, okay, C prime does not intersect itself transversely, but I can wiggle it away from itself so that it no longer intersects. This tells me that this squares to 0. I can do the same thing with the class C. Okay, so these fundamental classes not just give me a nice way to kind of understand this group structure, they also let me understand this algebra structure. So here's my singular cohomology as a Z2 algebra of my Okay, so more generally, you get if M is a n-dimensional smooth manifold and N is a k-dimensional smooth submanifold, then we get a fundamental class, some cohomology class in the cohomology of M, and the degree of this class is given by the codimension of the submanifold. Okay, and the one way to define these fundamental classes is using the Thom isomorphism theorem for the normal bundle. And in general, if X and Y intersect transversely, then we have this intersection product. Okay, so this is what I would like to replicate in the setting of Bredon cohomology. So let's return to example 1 to see how this might work. So I want to find codimension 1 or dimension 1 submanifolds that will correspond to these two generators. Okay, here are two examples of equivariant submanifolds, so submanifolds that are sent back to themselves under the action. So this circle is fixed, and then this red C, this is reflected when I do the action on the torus. Okay, topologically, these are both codimension 1, so I'd expect to get fundamental classes in H1. Okay, and if we were trying to figure out what bi-degree they should live in, then okay, we should probably look at the normal bundle. That was our lesson from our previous slide. So if I look at my C prime and consider the normal bundle, or a tubular neighborhood, to get an idea of the normal bundle, well, a tubular neighborhood of C prime, that looks like a cylinder. Okay, and really the cylinder looks like my C prime cross an interval with a reflection action. So that's C prime cross my R11, which is my sign representation. Okay, so I would expect this class for C prime to live in H11. Again, because the normal bundle for C prime looks like C prime cross a sign. Okay, we can do something similar for the class of C. We would expect it to live in H10, because here I have my C, and if I took some tubular neighborhood, it would look like C cross a trivial rep. With a fiber over these two fixed points, there you can see the trivial. Okay, I also can look at their intersection. We see this point Q here. If I take some neighborhood of Q, it looks like an R21. So I would expect a class there. Okay, and then I would hope to have some nice intersection product, which we end up having. So these two classes multiply to give me this intersection, which is this class of Q. Okay, so it turns out these classes do exist. We do a little bit of work, and with a bit more, just using these classes, you can arrive at the M2 algebra structure for this T1 with the reflection action. Okay, so this is very nice. In general, computations are hard, so it's in this theory, so it's very nice to have such a concrete way of understanding this M2 algebra. Okay, so this slide is somewhat misleading because it might make it look like these fundamental classes work just how they do in singular cohomology and everything kind of just goes through. I will say we got lucky in this example because all of our normal bundles were trivial. And so for trivial bundles, the Thom isomorphism theorem really just follows from the suspension isomorphism. There isn't much content there. So let's look at a different example to see how things might get screwed up when our normal bundles aren't all trivial. So in this example, we have a copy of RP2. So here I have my disk with the boundary identifications. I'm going to give this a C2 action by imagining sticking my finger down in the middle of the oval and then spinning it around. So when I do that, this point is fixed. But then also if I think about points over here, well, they get sent back around to points over here. So this boundary circle is also fixed. So my fixed set is S1, disjoint union upward. Okay, again, over here, I went ahead and put up the M2 module structure for the cohomology of this C2 space. Okay, so we want to try to find a fundamental class or a submanifold whose fundamental class generates this guy, and then hopefully use some intersection products to get the M2 algebra structure. Okay, so I've already drawn over here. There's kind of one-dimensional submanifold already drawn, just kind of staring at us. So that's this fixed circle, which I've labeled D. Again, topologically, this is codimension 1. So this should leave in by degree 1 comma something. Same for our Q. I have this fixed point. I would expect to get a class in 2 comma something. Okay, the normal bundle for D is no longer looks like a cylinder. Now this will look like a Mobius strip. But okay, if I pick any point in my D and looked at some neighborhood around it, it would look like that little that fixed interval cross a sine rep. In other words, this normal bundle locally looks like it's a locally trivial R11 bundle. So I'd expect to get something in H11. There is some work to do here. This isn't a trivial bundle. You really need to prove that there's some sort of Thom isomorphism theorem, but you can. Okay, and then same for Q. I would expect this to live in H2. All right, this class D will generate a free submodule by degree 1, 1. But we also want to be able to understand the algebra structure. If I look at my class D, if non-equivariantly, I could wiggle it so that it only intersects itself at a point. But equivariantly, I cannot do that. In general, making things transverse equivariantly is hard and not always possible, which is partly what makes stuff tricky. So instead, let's try to find a different submanifold. So I can draw a straight line across here. Remember, these points are identified. So this really is a copy of S1, this red C, and this has a reflection. Okay, again, I should get a class in H1 comma something. And what this something is what we need to figure out. So here's our normal bundle, or at least the outline of it. So it's this strip. Again, I see a Mobius band. I identify this with this side, but with a twist. But now we kind of see how things can get weird. If I look at this fixed point and look at some neighborhood around it, it looks like an R11 bundle. So the fiber over this point here is an interval with a reflection. If I look at this point Q over here, and I look at the fiber over it, I see a trivial representation. Okay, so something weird has happened. This doesn't seem to be the dimension of this bundle, this normal bundle, doesn't seem to be well defined. Okay, so we're even more confused. What should the weight of this fundamental class be? Okay, so let me tell you how this goes in general. So let's say X is an n-dimensional C2 manifold, and Y is a non-free k-dimensional submanifold, C2 submanifold, so sent back to itself under the action. Okay, then we would want to say we get a fundamental class for Y in the cohomology of X. The topological dimension should be n minus k, and then we need to figure out the weight is. So we did that as follows. We're going to consider the equivariant normal bundle of Y and X, so denoted this by E. Over each fixed point of Y, the fiber over that fixed point will be some C2 representation, right? So a C2 equivariant vector bundle, I should be acting on my vector bundle as vector bundle maps. So in particular, and acting over my action over the base space. So if my point little y is sent back to itself, then the fiber EY has to be sent back to itself. And then again, this action has to be through a linear map, so I really get a C2 representation. Okay, so this will look like R n minus k, that's the topological dimension, and then I have some weight. Now I want to let Q be the maximum such weight appearing over this fixed set. So I look at all my fibers over my fixed set and pick the largest weight representation appearing in the normal. Okay, and then the theorem is that we get a unique class that acts like a fundamental class. Okay, and really, and its weight is given by this Q, which was determined by the normal bundle as described in these 3 bullets. Okay, really this is a construction, and the theorem was that there's a Thom isomorphism theorem in this setting of Z2, or something like a Thom isomorphism. Okay, so here we were confused about what this weight should be. What the previous slide told us is we should look at the fixed set of our submanifold, so that's this point and this point. Over this point, the weight of the representation is 1. Over this point, the weight of the representation is 0. So I would expect to get a class in, okay, 1 is larger than 0, so in each one. Okay. The last thing, remember, we were trying to get this class in order to see what this cup product structure should be. So we wanted to use this intersection product. And so what we maybe naively write down is that the class of C times the class of D should equal, okay, they intersect at this point, Q. Okay, but something really has gone wrong here. This product is in by degree 1, 1 plus 1, 1, which is 2, 2, but Q lives in 2, 1. Okay, so this can't be right, but it turns out there is a modified intersection product that does hold. So if these intersect transversely in the non-equivariant sense, then this cup product is given by the class of their intersection, but maybe with some tau correction. Okay, and with a bit more work, you can figure out the M2 algebra structure. And by a bit more work, it's only using these classes and relations. I just haven't put them all up for time's sake. Okay, I wanted to show an example with free classes. I'm running low on time, so let me just kind of quickly say what happens when you have free submanifolds. So here we have a torus with a genus 2 torus with a rotation action. So we imagine skewering our torus through these 2 points and then rotating it on this spit. Here we have 2 fixed points. And now if we look at the cohomology, this is no longer free as an M2 module. And we have some of these A zeros appearing. But if we look over here, kind of our interesting submanifolds, codimension 1 submanifolds, also don't have any fixed points. So I can draw this green circle I've labeled C and look at its conjugate, which I've denoted sigma C. It turns out, okay, these classes, these submanifolds no longer have any fixed points, so I can't use the same trick to determine the weight of the classes. It turns out that these classes, or these free submanifolds, give us classes in every weight. So I get an infinite family of classes, all connected by some action of tau.
So the fundamental class for C will generate one of these A zeros, and then the fundamental class for D and sigma D will generate the other. And these also have a nice intersection product that leads to some kind of interesting product structures in the cohomology of these surfaces. Okay, let me just conclude since I'm running out of time. So the conclusion is we do have a working theory of fundamental classes with a nice intersection product. The construction relies on a version of the Thom isomorphism theorem, which I did not discuss in this slide, but is in my paper that's linked to this video. And maybe just to connect back to our prologue. So I had done these computations for C2 surfaces, and one of the theorems proved in this paper is that the cohomology of any C2 surface and constant C2 coefficients is indeed generated by fundamental classes. So these classes have a nice theory, and they really do help you understand these computations for C2 surfaces. Okay, I'll end there. So thank you for watching. If you have any questions, you should feel free to reach out to me via email. All my information is in this video information. So thank you so much.